Such a joke. It is recording. It did record. So probably shouldn't say anything too profane because it'll be recorded now. I'm trying to. You guys can't see it on the other screen. Yeah. I have witnesses though, Ethan, to that one. The reason we're waiting is I got kicked out on the other screen. I'm kicked out of the meet, so nobody knows what's happening right now. I don't get it. So annoying. Just a nightmare. What's that? For real, I think it might be that we were in this back corner of the school. I mean, I know. I'm looking right now to see if there's one even in there. Okay, now it's asking me if I can join the meet. You guys could try number 4. I mean, it's something. It's just picking up from yesterday. If you kind of remember all of that, or whatever number we're on, 4 or 5. I have no idea. Can you guys at home hear me right now? Okay, you're just a black screen. Okay. Did I just come back on, or have I been sitting here the whole time looking for no reason? Did you just get back, or I get back? Okay, good. Then I'm going to assume you can see me all right now. So we're on number 5. We're going to go quickly here now that we've given up that time. What we talked about yesterday is we kind of read through this. Radium-226 decay, so the amount is changing at A, so that's our equal to. So we're going to call DRDT, that's the rate of change of our radium at A, so equal to. When it talked about a rate, that's our K. When it talked about being proportional, that means it's a direct product to the amount that's present, so that is R. We did P's yesterday because it was population, same exact idea. What we did over and over again for the first 4 or 5 problems, we talked about how we could separate these variables. Yeah? Of course you can't. All right. And now it's not even letting, there we go. Everything's in slow motion right now, so. Okay, should be sharing here in a moment. I like that petition, Alex. We can go for that. Or a hotspot, right? Like actually then put something in my room to where I get some decent Wi-Fi. Okay, you can see me now or see my screen? All right, so what I just kind of highlighted the decaying is, that's what's changing. When it says at A, that's the equal to. The rate is your K. Proportional means it's a product. The amount present is your R. What we talked about yesterday, that's velocity. It's the amount of change over the amount of time. That doesn't do us any good if the question starts asking us about the amount. So what we did is we separated these variables. We went through the antiderivative, and every single time we integrate that differential equation, it always produced the law of exponential growth and decay, which is this. So we want to just recognize that differential equation, just jump right to the antiderivative, and then that's now what we work with. The next sentence gives you its half-life is 1,612 years, and then the question asks you how long is it going to take, so the variable that we're solving for, how long will it take for 1/4 of the given amount of radium-226 to decay? So similar to number 4 that we left off with yesterday, you're not given the initial amount at all. So because of that, you're going to leave this as R sub 0. But then what we did on the other side is we went ahead and wrote R sub 0. And yesterday we wanted to double our population in number 4. So yesterday, if I wanted to double the population, don't write this down, I would have put twice the initial population. What you have to understand about this one, because this one's actually a little bit tricky, what over here always stands for, that is the amount present at time t. So yesterday we wanted to figure out the time it took for us to double. So now read this one very, very carefully. It's asking you how long will it take for 1/4 of that to decay. So we don't want to be putting 1/4 of the initial amount because that's not how much is actually present. We want 1/4 of it to decay. So if 1/4 of it is gone, what we actually would have present would be 3/4. So you just want to read those carefully and make sure that we assign the correct ratio there, the correct product. Okay. From there, our issue right now, however, is this K we do not know. So not uncommon with these, same thing we dealt with in the first one yesterday. That means you were probably given other information that would allow us to figure out what the K is. And in this case, that information is this half-life information. So if I set up another one, we still don't know the initial amount. We're going to try to figure out K, and the way we're going to be doing that is by letting our time be 1612, because we know after 1612 years, whatever the initial amount was, we have half of that. Once these R sub zeros cancel out, we now have a way for us to go through and figure out what our K is. So we'll take our natural log of 1/2. That would cancel out the E on the other side. Divide by 1612. This is your K. I'm probably going to do it one time because I don't know if we'll have time to do all of them. But recall, this is probably now where you want to store this. So if I go to my calculator, natural log of 1/2 divided by 1612, we definitely need a calculator to evaluate that. And then whether you do the enter or not, you don't necessarily need to do that. You could have just hit store right away. I'm going to store that as my X. And then now my calculator has all those decimals. It's not rounded. So that is, I'm going to write this in red just so we know that this is actually a constant now. We know what that value is. Now we can go to this equation and start solving this for t. So take the natural log of both sides for this one. I should have left a little more room here. So I'm going to bring this over here. So we'll do the natural log of 3/4 would equal e to the xt. No, not xt, just the xt, because the e would cancel. And then do the natural log of 3/4 divided by x. And the x, again, is, you can just use your variable key because the calculator will know that it's that weird long decimal. And when we do that, you should get 669.04 years. So about as long as it took me to get class started today. All right. Okay, good with that? Well, I'll be dead, that's for sure. Sobering thought, really, on your Thursday afternoon. Yeah, go ahead, Pranav. Yeah, so it's the first sentence. So when I tell you that we have a certain amount of radium that's decaying, that means the amount is changing. So that is the change in our radium that's decaying compared to time. When you see at A, so to, so that it is equivalent to the rate, that's what K stands for. The word proportional, so directly proportional versus inversely proportional. Since this is directly proportional, that means it's a product. and then it's a product with the amount that's actually present. So whatever amount of R we have, we would be multiplying that by our rate. And then that's how we know, oops, it didn't change quick enough. That's how we know our rate of change, dr dt over, the dr over dt. Okay. All right. Number 6. Usually I have you kind of walk through this, see if you can figure this out. We're going to jump right to it. So number 6, it says, electricity is draining from a capacitor at A. So again, here's our electricity is changing at A, so equal to a rate, K, that is directly proportional to the voltage across its terminal, and then our T is measured in seconds. And then they actually give you this differential equation here. All I want you to do in part A, and this is where I usually have you do it, but we'll go right to it, solve that differential equation for B. What we don't want to have to do is do all this work. We don't want to separate those variables. We don't want to do the antiderivative. What we should hopefully understand now after doing a bunch of these is when you see this differential equation, every time this would have gotten integrated, it produces the law of exponential growth and decay. And the nice thing about this one, isn't this always our K? Like whenever we solve this, that was your K. So we actually know what our K is. It's a negative 1/40th T. If you want to separate these, if you want to multiply by dt, divide the v, do your antiderivatives, and go through with all those substitutions, that would work. But long term, we just want to understand this is what we're always going to end up with. Okay. So now what that then gives us is a way we can answer letter B, because now the question is, how long will it take for the voltage to drop to 10% of the original? So the question is asking you for your time. We know our K now, so T should be the only variable we're left with. You're not given the amount, the initial amount, so we're going to leave this as V sub 0. So it's another one where we're going to have to multiply the initial amount. So now read that very, very carefully. This I do want you to think through because it should only take 15, 20 seconds. And decide, am I multiplying the initial amount by this 10%? Or am I multiplying that initial amount by 90%? And then just keep in mind, what this always stands for is the amount at time t. And then that will guide your decision. All right. Ethan has waffled. He gave me both. So what are you going to go with? He says final answer 0.10 V sub 0. Do we agree? A lot of us are saying yes. Yes, that is correct. We want it to drop to 10% of its original value. So we're looking to see when do we have 10% remaining. So we multiply by 10%. If you do that, then it's pretty straightforward from there. Not too bad. If you have a calculator to solve this equation, the V sub zeros will cancel. Take the natural sides. So then T should equal the natural log of 0.10 divided or multiplied by negative 40. Okay. Oh God, it was like 90 something maybe, if I remember correctly. Yeah, that sounds right. 92.1 what? What is it? I know, but we need 3 decimals. Okay, and then seconds. Sorry, I did them all with the calculator 5th period, but I want to kind of speed this up, so sorry. Plug that in. We should be able to plug that in. Should get 92.103 seconds. Okay? That we should all be alive for, hopefully. All right, then the last thing. And these are a little messy. There's a lot going on with these. So it's called Newton's law of cooling. here's what Newton's law of cooling is based off of. So see if this is intuitive to you, see if this makes some sense. So it says a pizza gets removed from an oven is going to cool to the temperature in the room. So that's pretty obvious. It says in similar situations, the rate at which the objects, so in this case, the pizza's temperature is changing in any given moment, is roughly proportional to the difference between its temperature, the pizza's temperature, and the temperature of the surrounding environment. So what that means, if I pull a pizza out of the oven at 350 degrees, and let's say the room temperature is 70, initially the rate's going to be very quick because the difference between 350 and 70 is pretty big. So it's going to decrease very quickly the temperature. But as it gets down to like 100 degrees, now that 100 degrees is close to 70 degrees, it's still going to continue to decrease towards that room temperature, but not as nearly a quick of a rate. All right? Does that kind of make some sense? Just living your life for 16, 17 years, hopefully that makes some sense, and you already would have known that. Okay? So what we want you to now do, this is what Newton's law of cooling is based off of, that idea that the rate is going to be basically dependent upon the difference between the temperature and the surrounding temperature. So letter A, if T is your temperature of the object and T sub S is the surrounding temperature, I want you to write a differential equation to represent this situation. And again, I hate to take the joy of math away from you where you can think about this and figure this out for yourself, but we're going to jump right to it so that we can finish. So our differential equation, we're going to say, I'm going to use a capital T in the numerator, lowercase t in the denominator. So it's the change in temperature over our change in time. Our rate is our K, and it is proportional to the difference between its temperature and the temperature of the surrounding environment. So if you remember sum, difference, quotient, all that good stuff, difference meant it was the difference, so subtraction, between the pizza's temperature and the surrounding temperature. Okay. So we could, in terms of how quickly our temperature changes with respect to time, is whatever that constant K is multiplied by the difference between our pizza and our room. So that's the differential equation that we are setting up here. Okay. Then what we do is based off of that idea, again, this is kind of like a velocity right now. If I actually now start asking what's the temperature of the pizza, a velocity doesn't do us any good. We would want to solve this. So what I want you to now do down here, now we are going to go through this work because this is different than exponential growth. So rewrite this. And what we're now going to do is go through all this work. So we're going to separate those variables, so multiply the change in time over. These t's need to get divided over. So we would have dt over t minus t sub s. And then that would equal k dt. Now that they're separated, we would do the antiderivative of the two sides. Do this over here. When we're talking about this model, even though it's based off of the assumption, even though it could fluctuate a little bit, that the surrounding temperature is a constant. So like the room right here, right now, while it fluctuates just a little bit, for the most part, it's probably 70 degrees. So our understanding that this is a constant, what we're really looking at over here, it's kind of like having 1 over t minus 6. If I ask you for that antiderivative, wouldn't that just be the natural log of minus a 6? All right, so that t sub s is our 6 in this case. It's our surrounding temperature. So the antiderivative left, we would say, is the natural log of t minus the constant t sub s. The antiderivative of k would be kt, and then plus our constant. I'm going to use the e to get rid of our natural log. And then we get our little shortcut over here. That should then just become c e to the kt. And then our initial condition is here. And what this is basically just telling us, if we let our time be 0, so be a 0, then what this variable right here stands for, that's what that is. That's the temperature at our particular time. So since my time is 0, I'm going to write that as my temperature at time 0. So that becomes t sub 0 and then minus t sub s e to the 0 is a 1, so these all just become a 1. And what I get for my c is t sub 0 minus t sub s. So it's a weird looking c, but that nonetheless is our c. So if I now go back to this equation right here, this is Newton's law of cooling. Minus t sub s equals, and then now instead of c, I know what c is. It's that difference between t sub 0 and t sub s. And then e to the kt. Depending on what book, what resource you look at, when we solve the differential equation, we get this. Notice how in this model, rk is positive. It doesn't necessarily matter, but most books, just to draw a parallel to the idea that we're cooling, this is the exact same formula, but notice how they assign a negative to the k. We don't know what k is. It could be positive, it could be negative. That's why it doesn't matter. But our book, so this is why we basically go with it, it assigns that k as a negative because we're cooling. So this is Newton's law of cooling. This is what we use now to solve questions with this idea in mind. Okay, so hopefully we can at least get through one of these. So go to number 7. Let's start by just writing this down. All right, so there's our general formula. We got a lot of moving parts here. Actually, let's make sure we understand what all these things mean as well. So you don't need to change yours. I'll mark this one up. So when we go through all these variables, the t is your time still, k is your rate, t sub s's are our surrounding temperatures, t sub 0 is our initial temperature, and then this is our temperature at whatever time we're evaluating it at. Okay, so as we now go to set this first one up, it says a hard-boiled egg at 98 degrees Celsius is put into a pan under 18-degree running hot water. So right away, let's assign some variables. So we have a hard-boiled egg, and its initial temperature is 98. So that's our initial temperature. We're throwing it in for T sub 0. We're going to try to cool that down. The way that we're going to cool that down is by putting it under water that is measuring 18 degrees. So that is then the surrounding temperature that we're using to cool the temperature of our egg. So we put that at T sub S. The next sentence, we are then given a time. So if you are now given a time of 5 minutes, the egg's temperature is found to be 38 degrees. So if I let my time be a 5, then my at that time is 38. So what we're missing right now is a K. So we actually have an equation right now that would allow us to solve for K. We'll get to the actual question here in a minute. So let's go through here, figure out what our K is. So you get 20 equals 80 e to the negative 5K. Divide by the 80, so we get 1/4 equals e to a negative 5K. Take the natural log, both sides, and then divide. And what our K would equal is the natural log of 1/4 divided by a negative 5. The store option, again, pretty critical. You now want to store this in your calculator. All right, so this is our K. Not our answer though, because now we go to this next part and try to leave a little room to operate here because we're actually going to set up a couple more equations. The question asks, how much longer will it take for the egg to reach 20 degrees Celsius? So set up another one of these guys over here. And then if we have time, I'm going to show you another way that we could have done this that a lot of people would do. Because there's two routes that we can now take. We're going to do it the shortest and quickest route, but my guess is a lot of us would kind of do it the little bit longer route that requires a little bit more thought. The question is asking us, how much longer will it take for the egg to reach 20 degrees Celsius? So what we're looking for right now, we have our, let me change the K to an X. So keep in mind, we know what K is right now. It's whatever this value would have been over here. We're looking for our time. So T should be the only variable in play. The surrounding temperature hasn't changed. That's still definitely going to be the 18. And then now here's where you have to make your decision. Because you could do one of two things. You could say that your initial temperature was this 98, and then we're ultimately looking to see how long it takes to get to 20. So if you do it this way, and it's not the way I'm going to do it, this would have been the or. If I do 98 to 20, the time that you're now solving is for the overall time that would have elapsed to get you from 98 to 20. That's not necessarily the answer to the question, though, correct? The question is, how much longer would it have taken after the first 5 minutes before we would get that temperature of 20? So while this would work, you just have to be careful how you answer that question. I'll explain what that means here in a minute. So what we're really looking for the amount of time that it took to go from 38 to 20. So I'll put the 38 right here. Now the time is going to figure out how long it took us to go from the 38 to the 20. That is ultimately the answer to the question. Okay, so if we go ahead and solve this, so again, hopefully we can all do this. Hopefully I'm not doing this too quickly or I screw it up. We should get the natural log of 1/10 divided by the negative value of x that we have stored in our calculator. When we plug this into our calculator, what that is going to give us is 8, and I'm going off of memory with this decimal, so if it's a little bit off, sorry for those who have a calculator plugging this in. It was 8.305. The decimals are off a little bit, sorry. Okay, that's good. Now, understand if you would have done it the other way, so don't change your work, because we're going to run out of time. If we had time, I would show you both ways. If you would have gone from 98 to 20, so from the original temperature overall to the 20, the time you would have gotten was 13.305. And what you would have had to have understood is that I needed to subtract away that first 5 minute interval, and we still would have gotten the 8.35. That was our final answer. Okay? Okay, let's stop there. It'll give us something to do tomorrow. We'll do number 8 tomorrow. Be more than one of those because there's a lot of things going on with these. So bring this tomorrow. We'll get this finished up tomorrow, and then we'll start with the reviewing and assignments and everything for the test Wednesday. Okay? Okay, we'll see you guys. Have a good day. So first of all, it doesn't have to be. In many books, it won't be negative. The reason, okay, see you guys. The reason you'll see a lot of books put the negative in front of it is because it's called new cooling, and the idea that we're getting smaller means we have a negative rate. So it just throws a negative in front of the K since the K stands for our rate. Okay, see you, Sean. Does that make sense? And I guarantee if we went back and we did that with a positive, if we went back and did it with a positive K, you would get all the exact same answers. Okay. Okay. Hey, Luke, will you do me a favor? Oh. Did he? Okay.